Welcome to another live session in our MOOC, and I see Matthew tells me that we're brimful of questions, so I'm looking forward to answering them and anything you bring to me live.
So the first question is from one of the mentors in our Coursera class, and says that many students have difficulty understanding what flat means and whether it means two-dimensional, but I believe this is in terms of the flatness of the universe problem.
Right. So the geometry of space, it's a pretty fundamental question in cosmology. And it arises, of course, because of general relativity. So to give the quick historical context, Newtonian gravity is built on Euclidean space. It's based on the type of geometry you learn in elementary school, the simplest form of geometry, where angles in a triangle add up to 180 degrees and light travels in straight lines through space. The real universe we live in is governed, as we now know, by general relativity. And general relativity accommodates space curvature. In fact, space curvature is built into the theory because the theory equates the curvature of space-time, a hyphenated entity, with the density of mass energy, another hyphenated entity, incorporating the fact that these things are coupled. And so general relativity accommodates the fact that the universe can be curved. Now we know that space-time can be curved locally or on small scales by intense gravity. That's what happens with a black hole and also with neutron stars and pulsars that are very compact. But general relativity applies to the cosmic realms of space-time, and so general relativity includes the fact that the entire universe, the visible universe seen by telescopes, could have a curvature. In the formalism of general relativity, the curvature essentially has two signs. It can be positive or negative. A positive curvature in two dimensions, because we can only imagine this really in a smaller number of dimensions where we can have a model that we can hold like a sphere. That's a positively curved two-dimensional surface, and you know that the angles of a triangle drawn on the surface of a sphere or globe like the Earth or the Sun add up to more than 180 degrees. Negatively curved space in two dimensions corresponds to a saddle that sort of extends infinitely in each direction. If you drew triangles on a saddle, the sum of the angles would be less than 180 degrees. So that's the distinction between positive and negative curvature, and zero curvature corresponds to the special Euclidean case. So general relativity accommodates space curvature either sign, positive or negative, and any amount. And it's a question for observation whether the universe we live in does have global space curvature. Experiments until the microwave background satellites went up were not very effective at measuring space curvature. But microwave background radiation gives us a sight line across the universe going back to 400,000 years after the Big Bang. So we can essentially see radiation that's traveled across the entire universe. And since the speckles or fluctuations in the microwave background have a characteristic angular scale of about 1 degree, we can see whether that angular scale in traveling across the vastness of our universe has been amplified or de-amplified. And it turns out that it hasn't. Relative to a model, it's not de-amplified or amplified, and indicating that space is flat. So there is no global curvature to space-time, and that's an accurate statement at about the 1% level. So what that means, for example, is that if you send two parallel light beams off from the Earth through the universe, they would neither move closer together, converge, nor move further apart, diverge, which would be positive or negative curvature. They would stay parallel forever, as far as we can tell. So that's what observational cosmology says. The trouble is we have to imagine curvature in 3 dimensions of space, and since we live in those 3 dimensions, we don't have a visual analog. We have to drop down to 2 dimensions to use things like saddles and spheres as our 2-dimensional analogs. But that experiment has been done. It's one of the most accurate measurements in cosmology. And the fact that the universe is globally flat is somewhat of a surprise in cosmology, and it's part of the ammunition for the belief that there was a very early rapid exponential change in the size of the universe, a period called inflation, which would act to flatten out space-time to the point where we could not detect any curvature at this late time in the expanding universe. So flatness of space is not convincing evidence that inflation happened, but it's a natural consequence of something like the inflationary event.
Okay, the next question is from Val, who is on live. And she asks, there are 2 kinds of white dwarfs. And I'm going to try and summarize. Does the Chandrasekhar limit apply to both types? If so, would one explode with more energy than the other? Are both involved with type 1a supernova? Can you discuss and clarify how the two types are different?
Right. So that's a good question. It's a high-level question because most people don't distinguish between white dwarfs. The major distinction, without getting very technical and well beyond the level of the course, is to say that the chemistry of the stars that lead to white dwarfs can vary. In other words, we can have a white dwarf resulting from, say, a star like the Sun, which at the end of its life has really not gone much beyond creating helium from hydrogen. And so that's a white dwarf, a collapsed, degenerate state of matter, to use the physics term, that has very little carbon in it, because the Sun is simply not massive enough to be hot enough late in its life to make a lot of carbon. But there are more massive stars than the Sun that will still die as white dwarfs, that do go through fusion stages that lead to carbon, substantial amount of carbon fusion. And so those are carbon-rich white dwarfs. So the fundamental distinction of these two types of white dwarfs is white dwarfs that are carbon-rich and not carbon-rich. And the more massive stars die as carbon-rich white dwarfs. That's a very strange state of carbon, of course. It's a highly dense form of carbon, and people have said it's diamond-like because actually, to a solid-state physicist, it is in a quasi-crystalline state. Pink Floyd referred to this when they wrote that song, Shine On You Crazy Diamond. The crazy diamond there, of course, was talking about Syd Barrett, founder member of their group, who died young and insane, and only was with him for 2 albums, but it also refers to the quasi-crystalline state of a white dwarf. So those are the two rough kinds of white dwarfs. And then the question as to whether the Chandrasekhar limit applies to both is that yes, it does. The Chandrasekhar limit is a limit based on surface gravity, essentially, and is independent of chemistry. So the Chandrasekhar calculation doesn't really care about the material that the white dwarf is made of. It just cares about the amount by which that material has been compressed and how the surface gravity is calculated.
Okay, next question is again from someone who is on with us live. What's the cause of moons of a planet moving in opposite directions? For instance, Phoebe around Saturn.
Yeah, that's a good question, because mostly moons are very systematic in their motions, in their orbits. For planets that have multiple moons, generally those moons are orbiting in the same direction that the planet is spinning, and those moons are generally occupying what would be the equatorial plane of the planet. That is to say, their angular momentum vectors are aligned. So that's an overall degree of regularity that we see especially through the moon systems of the 4 gas giants. Phoebe, as an example, and not the only one, but one of the bigger ones, is a counter-rotating planet going in the opposite direction. And to an astrophysicist or a dynamicist, that essentially shrieks out that this must have been a captured moon. It's possible more generally for moons to be captured by planets, but it's a fairly rare occurrence because space is so empty. Most moons are formed at the same time their planets are formed. But when we see a counter-rotating moon, or a moon with a very high ellipticity relative to the equatorial plane of the planet, or a moon that has a high, either a high ellipticity or a high eccentricity, either of those things, then it's suspicious that that moon may have been captured from interstellar space. And that's the case with Phoebe, as far as we know. But proving that hypothesis is, of course, quite difficult.
Lori, who is on live, asks, can you comment on the molecular oxygen found on Comet 67P Churyumov Gerasimenko? I have read an article suggesting that the finding brings into question what we know about how the solar system was formed, and how does molecular oxygen found on a comet affect what we know about our solar system.
Right. I'm not going to comment in detail on that because I haven't read the research paper that it's based on, and I don't like to base my comments just on news stories because they don't always get the science right. So molecular oxygen, is anticipated to be a component of comets. Comets, of course, remember, are made of rocks and ices, and our more recent information about comets suggests that they're rather loose aggregates of rocks with perhaps a larger fraction of volatile material, frozen volatiles, which is carbon dioxide, methane, water ice, and so on, than rocks. Now, some of those molecules, those volatile materials, of course, incorporate oxygen, and the oxygen can be freed by high energy interactions. Remember, these are exposed naked rocks, so cosmic rays are raining in. There are small particle hits, micrometeorites, and so on. So there's plenty of energy hitting the surface, and that energy can, in occasion, liberate free oxygen from the gases that contain oxygen, or the rocks that contain oxygen, and that free oxygen, being very reactive, will then combine with other minerals or other substances. So the simple answer is I don't think the astronomers, the astrochemists, really know how to interpret that oxygen signature because of all different ways that oxygen can react. But the presence of that oxygen in that amount that was detected in the Comet 67P, which, notice, using the abbreviation, I finessed the fact that I can't pronounce the Russian word either. That is definitely something people are wanting to follow up. It's a telltale of a very interesting ingredient of primordial solar system material.
Right, the next question is from Tyler Morrison, who's on with us live. What if the Andromeda galaxy's velocity increases from the interaction with the Milky Way's gravity, and as it gets closer, what is going to happen with that?
Yeah, it's a good question. It's going to take a while to play out. So the current net velocity of us towards Andromeda is about 100 kilometers per second. That's a fairly modest net velocity for two galaxies to have. It's about equal to the random velocity any two galaxies will have in the nearby universe. For example, in a rich cluster like the Comet cluster or even the Virgo cluster, the velocities galaxies have with respect to each other are more like 500 or 1,000 kilometers per second. So it's moving towards us rather gently. And if you just take the distance and divide by that speed, assume it doesn't change, then you come up with this estimate of about 3 billion years before the interaction and merger. And as the question suggests, there will be acceleration as the two galaxies approach. It's very unlikely that there will be a direct collision, nucleus to nucleus, of the two galaxies. It's a little hard to estimate the full trajectory because we don't measure the three-dimensional space motion. We measure a radial velocity and have to model the other two components. So we can't put an exact vector on Andromeda's motion relative to us. But it's fairly close to a collision. But it'll probably be a glancing encounter. So the galaxies will indeed accelerate as they get close, and the two galaxies will swing by each other in an accelerating dance, if you like, that acts to throw off arms of stars from the disks of the two galaxies. It's not yet clear whether, from our, partly because of this uncertainty of the vector of the motion, what will happen at the position of the sun. So we, of course, in 3 billion years will have gone around the galaxy another dozen or so times, so it's very hard to say exactly where the sun will be when the two galaxies meet relative to their collision path. It's an equal coin toss whether stars in the region of the sun will be tossed out into a lazy arm of stars that extend maybe 1 million light years away from the two galaxies that are merging, or be tossed into the star pile of the two galaxies that do merge. So after that accelerating first pass, the two galaxies will settle into a sort of tight death spiral, if you like, where the nuclei of the galaxies, being the most massive parts, will essentially spiral towards each other. That will be a slow process taking several 100 million years. Meanwhile, the outer parts are being heavily disrupted by tidal forces, which are very strong when two massive galaxies meet. And those stars that are tossed out into arms, there'll be other stars tossed out, maybe several waves of the ejection of loose arcs of stars into intergalactic space, some of which will be liberated from the combined system. So people have simulated this, of course, with supercomputers, and you can find those simulations online, but they depend on the initial conditions. So, when you see one of those simulations, remember that they had to assume something quite specific about the trajectory, especially of the two galaxies. The speed is, of course, measured. And the outcome is very sensitive to those initial conditions. So they would have to run dozens of simulations to accommodate all the possibilities.
All right, the next question is from PJ Lewis, who is on live. Given that spacecraft have been launched from the Earth for over 60 years, and that all materials used in their manufacture effectively reduce the mass of the Earth, is it possible to measure the infinitesimal change in the Earth's orbit?
That's a nice thought. You know, where we're putting things into Earth orbit, and of course, some of them have left the Earth system. So, of course, the things that are in the caveat on that question, of course, is that the stuff we put into Earth orbit has not left the Earth sun. It has not left the Earth's sphere of gravitational influence. So it's not attached to the Earth, but it's still part of the gravitational envelope, if you like, that you would draw around the Earth of things that are bound into its orbit. Even if it were an important effect, the amount of that stuff, the total amount of stuff we put up there, I mean, it's really hard to estimate, but and even if it's, I think it is several thousand tons of space debris, maybe 10 or 20,000 tons, I'm not sure. That is such a tiny fraction of the Earth's mass that I think it is truly a negligible effect, but it's an interesting question.
Okay, the next question is from Mike C., who is also on live with us. What is your opinion, or the popular opinion, as to why we had an ice age approximately 11,000 years ago?
Well, that's a big question for the geologists and climate scientists. So I don't know, and the truth is I don't think anyone knows exactly. The trigger of ice ages is understood in very general terms. There are so-called Milankovitch cycles, which are they're sort of resonances, if you like, in the very subtle orbital variations of the Earth, Sun, Moon system. And those imply cyclic variations with characteristic timescales like 26,000 years, 100,000 years, and periodicities in the climate record. And people have argued now for 20 years about whether periodicities of any time scale, like tens of thousands of years, are seen in the climatic record. There's slight evidence for some, but basically the strongest predicted Milankovitch cycles do not show the strongest potential signatures in the climate record. So the jury is sort of out on this, where there are a set of dynamical orbital effects that should change Earth climate in a repeatable way, in a sort of quasi-periodic or periodic way on these long time scales. But those signatures are just argued about because the record of tracing them is imperfect and has errors, or because the strongest signatures that you predict are not the signatures that are seen. That's a long answer for the fact that the timing of the last ice age does not neatly sync up with any one of these periodicities. So there's no clear astrophysical trigger for the last ice age. Also, I think part of the problem of prediction, post-prediction, if you like, looking backwards to explain events in recent climate history, is that these episodes are very nonlinear. Because when you start to have a feedback loop, which is often happening in climate change. So I'll give you one. We know of some examples in the modern concerns about climate change, but one is, for example, that when the Earth heats up, the ice pack melts, and ice reflects more sunlight than dark material, and so the Earth absorbs more heat, which helps it heat up more, and so that's a positive feedback loop that affects climate change. And these positive feedback loops are the hardest things to model because they're nonlinear effects. And it's almost certain that the trigger of ice age is a nonlinear trigger, and that means it's very hard to model. So there's very poor power prediction on ice age, looking backwards of saying, why did an ice age happen at this particular time? And even the ending of an ice ages are not clean, simple things that happen for 100 years and then go away. Usually an ice age is a series of episodes where, you know, if you're plotting mean global temperature, there's an overall deep trough, and then there are spikes within that trough where the climate can warm up substantially, almost to its non-ice age level, and then it kicks in again. So the fine structure, if you like, of an ice age can happen at the sort of century level, whereas the ice age itself is happening on a sort of millennial time scale. It's really too complex to be fully understood by climate scientists yet.
Okay, the next question is from Val Parks, and again, he is on with us live. And Val asks, what exactly is a graviton? And if it is a theoretical particle exchange between particles with mass, how can this be? So how do these exchanges work?
So graviton is a hypothetical carrier particle for the gravitational force. So in the standard, as you all probably know, the standard model of particle physics does not actually fully accommodate gravity because we don't have a quantum theory of gravity. So you have a standard theory of particle physics that's based on the quantum properties of subatomic fundamental particles, and you're trying to pull gravity into the mix, and it hasn't yet been done. But in anticipation of the fact that it could be done, people have hypothesized in the so-called standard model of particle physics that for each of the four fundamental forces, there's an exchange particle. The most familiar of these, of course, is the photon, which is the exchange particle or carrier of the electromagnetic force. And within the nucleus of an atom, holding it as a tiny impenetrable fortress, essentially, the carrier particle is a gluon, which is the exchange particle between the quarks that form protons and neutrons in the subatomic nucleus. The exchange particle for gravity, by far the weakest of the four fundamental forces, is analogously hypothesized to be a fundamental particle called a graviton. In quantum theory, it has a spin 2, and it's a boson because it has integer spin. Remember, photons are also bosons. So the carrier particles or exchange particles are always bosons, while the particles themselves in the standard model can be either bosons with integer spin or fermions with half integer spin. So the theory accommodates a graviton with integer spin, a boson, and in the theory, yes, this gravity force propagates with the speed of light. And that hypothesis has never been tested, but it's been tested imperfectly in the lab. So testing gravity traveling at the speed of light is really hard to do because, of course, logically, you have to switch on gravity and switch it off again to see how fast its signal propagates. And it's not something we can easily do to make mass just disappear. We can change it into energy, but then energy has an equivalent mass by equals mc squared, so you haven't necessarily got rid of the mass from the situation. So the standard model of particle physics has these untested propositions that there is a graviton, and none has ever been detected, that gravity through gravitons propagates at the speed of light, and there have been some indirect tests of that, but no, really good and convincing tests. And therefore, we are missing a piece of our gravity theory. These are just speculations that haven't been proven yet, and so the model is still in doubt.
Okay, the next question is, actually, to follow that up, do gravitons, are they affected by black holes? Like, would they not be able to escape the clutches of a black hole? How would that work?
Right, that's a very good question, because if the graviton is the force carrier of gravity and a black hole exerts gravity, then gravitons should be emitted, if you like, by a black hole. So, and that's a great question because it hits one of the contradictions that's built into the heart of the theory. Yes, in principle, gravitons do escape a black hole because the black hole exerts gravity. And yet they're traveling at light speed, and the black hole, by definition, has no information leaving it. The simplest answer to the question, but it's a great question, is Stephen Hawking said black holes contain the seeds of their own demise. And he was aware, as a great architect of black hole theory, of a number of situations where black hole theory is essentially pointing to problems in gravity. One of them is that question, the question of how does the black hole propagate its gravity as a fundamental particle force when nothing is supposed to leave it. A second is any model of a black hole points to a singularity, an infinity of mass density at the center, and that's non-physical. That means something's wrong with your theory when you predict that. And those are just two examples. Then there's the information paradox, which there's a lot of debate in the theoretical community as to whether that is a fundamental problem of black holes or just a misunderstanding of existing theory. But the consensus at the moment could be that it's a fundamental problem for black hole theory, in which case that's yet a third thing that's wrong with black hole theory, which is to say gravity theory.
All right, the next question is sort of a pair of questions, one from email, one from a live session. Is there a figure for the total mass of black holes in the universe? And are these black holes considered normal matter, dark energy, or something else? And then what's their relationship to wormholes, and do wormholes really exist?
Okay, so that's a good question. The census of black holes in the universe. What is the mass of black holes relative to other stuff? I've never seen that as a single number, but I can actually pretty easily calculate it because I know the two pieces that go into it. The supposition is that black holes are normal stuff, because a black hole, whether it's one at the center of a galaxy, a massive one, or the remnant of a dead massive star, is composed of normal star stuff, just super compressed. So it is not thought that black holes are any exotic form of matter, with the exception that physicists have talked about quark matter, have talked about situations of extremely high density of matter, such as might pertain inside a black hole, where quarks are actually liberated in a way that they aren't in the atomic nucleus. But either way, those are still normal particles. So let's consider black holes normal stuff and not dark matter. Some dark matter could be part of what forms a black hole, but the dark matter interacts so weakly by electromagnetic forces and only by gravity that in the end, in a black hole, not much of the stuff is going to be dark matter. So we consider it normal stuff. So how much normal stuff? Well, in a galaxy like the Milky Way, where we understand the stellar populations, and where, depending on where you cut off the mass, we estimate 200 or 300 billion star masses worth of stars, most of which are red dwarfs or puny stars, there are roughly expected to be 20 million black holes. So that's 20 million times the mass of the sun in normal dead star black holes in the Milky Way. Remember, that's 20 million out of 200 billion. So it's a very small fraction of the number of total stars, because black holes form from massive stars, which are quite rare. At the center of our galaxy, if we take our galaxy as typical, there's about a 4 million solar mass black hole, a single black hole that has 4 million times the mass of the sun. So there's about 4 million solar masses worth in one black hole, and about 20 million solar masses worth in small black holes. So that's like 25 million solar masses worth of black hole. And then the mass of the entire galaxy, if you want to put in the dark matter, which you do have to do because the galaxy is held together by dark matter, the mass of the entire galaxy is more than that 200 billion times the mass of the sun. It's getting closer to 1 trillion times the mass of the sun. So you can see that 25 million solar masses in black holes relative to the overall mass of the galaxy is a really tiny fraction. It's like 0.1% or less. So black holes are present in and in other galaxies we anticipate a similar situation. So I don't think there's any kind of galaxy where the black hole stuff dominates the galaxy.
Okay, the next question is from Jackie Wu, who is on with us live. And the question is, do you think it is risky to search for aliens?
Well, Stephen Hawking does. I'll give my opinion in a minute. He's been on the record as saying that maybe the listening search, which is most of what SETI, the Search for Extraterrestrial Intelligence, does. It uses radio telescopes just to listen for artificial radio signals from hypothetical aliens on planets around sun-like stars. The listening experiment, which is a passive experiment, I don't think that's risky, except how would we react to the information if we found we were not alone? But some scientists in this area, of course, are doing transmission experiments too. They're beaming signals into space. They're using pulsed lasers or klystrons to send powerful radio signals into space, using the radio telescopes essentially to beam things rather than just receive them. And that's the kind of experiment that Stephen Hawking, and actually a group of scientists also last year, there was a petition, I think Jeff Marcy, Bill Gates, there were some fairly famous people that came out also saying that we should maybe hold off on doing this until we'd matured a bit, and really did we want to betray our position in the universe to unknown creatures of unknown powers. I mean, my own opinion is that the probability of success of that experiment, the probability of contact, is so low because it's almost certain that the galaxy is maybe moderately thickly sprinkled with life in terms of microbial life on habitable worlds, but it seems to be fairly thinly sprinkled with intelligent life and civilizations, or simply we would know about it. It's the Fermi question. So in that sense, given the success of the experiment being very low, the risk presumably is also low. So I don't see any problem with doing the transmission experiment. But it's a way to get a good argument going, even in a room full of astronomers, if you raise that question.
Okay, Tom Story, who is on with us live, asks, if acceleration is defined by a change in direction or a change in magnitude of a vector, does light accelerate in a gravity lens?
That's a good question. Yes, in that sense it does, because even though within the context of special relativity, light is always traveling at the same speed, that's essentially a foundational proposition of special relativity, the deflection of light indeed corresponds to an acceleration formally defined. And in fact, gravitational radiation is a sort of consequence of that acceleration. If you have a changing mass, then you will have gravitational radiation. So the change of state of mass leads to acceleration for gravity, and that should also be the case for light. Because remember, light has an equivalent mass, so you can just think of it as well, equally well, as a sort of particle that's having its direction changed as it moves, which is acceleration. So yes.
All right, we have a couple of people who've asked this question, one via email and one on our live session who's with us now. And it has to do with light travel time and looking back. So let's say I'm currently 100 light years away from Earth. I have a super high resolution telescope. Am I correct in understanding that means that I will be seeing the planet as it was 100 years ago and not as it currently is?
Right. So I'm assuming that you're on the Earth doing this measurement rather than 100 light years away looking at us. But either way, it will be the same thing. If we, with our super high resolution telescopes, which we don't really have yet, are looking at an Earth-like planet 100 light years away, and we found such planets, we are indeed seeing them as they were 100 years ago, because the radiation that tells us their existence is 100 years old as we receive it. And the same would be true in the opposite direction. If someone, an intelligent civilization or alien on this Earth-like planet 100 light years away is looking at us, they would be seeing us as we were 100 years ago. So before the space age and before the two world wars and so on. And that, of course, means that the communication between entities that are separated by this distance is slightly tortuous. You know that dealing with the Mars rovers and landers involves a long time delay between 15 and 35 minutes, depending on where the Earth and the Mars are in their orbits, for a signal to travel to and fro, which really means that the rovers have to work autonomously. You probably notice, if you've both read The Martian and seen the movie, in the movie, because it would be really clunky in the movie to have to keep waiting for half an hour to have an exchange, you see Watney, the astronaut, and the NASA sort of typing away on a console, having real-time communication. So in the movie, they kind of just, I mean, obviously they knew that was really wrong, but it doesn't make for a very good movie to forget that. Now, if you've got two civilizations 100 light years apart, it's 2 centuries before you can have a single round-trip communication. So that's kind of slow going, and probably doesn't make for a good conversation.
All right, Mike C., who is on live with us now, asks to put a satellite in a stable orbit around Earth. Its mass is the key variable as to what altitude it must be. And has the ISS had to change its altitude as its mass increased over the years by adding more to it? So he's got this question about orbital dynamics and how do these quantities of mass and altitude relate to orbits around objects around the Earth? Right.
Well, they don't strictly relate, because it's the speed that dictates the nature of the orbit. And that's easy to see, because if you have a space station, say, just use your example of a space station, just say that in the interior compartment of one part of the space station, there's a huge heavy weight of some kind attached to the wall of the space station. Well, if you detach that weight from the wall of the space station, then it will just float around inside the room you detached it from in a weightless way, and you would be weightless as the astronaut witnessing this, and the orbit of neither part would change. So logically, that's what they call a thought experiment, Gedanken experiment in Einstein's term, to show that it's the orbital speed and therefore the energy of the orbit that keeps the space station where it is, and the objects within it share its same speed, and so they share its same orbit. So there wouldn't be no change if you add or take away a piece from the space station, as long as it's all moving the same speed. Now, the complication for the space station, as for the shuttle, as for any low Earth orbit, is that low Earth orbit is not really completely free of the Earth's atmosphere. There's an extremely diffuse, very low density component of the Earth's atmosphere that extends, the exosphere, that extends well out into space to low Earth orbit distance. And so the ISS is subject to a small but steady drag because of that extremely diffuse tail of the Earth's atmosphere. Because remember, it's in it all the time, going around and around, endlessly, thousands and thousands of times. And the net effect of that, of course, is to degrade the ISS orbit. And so the ISS, as other low Earth orbit objects, would eventually decay and fall into the Earth. And that's, of course, the prospect that the ISS has to deal with. So all low Earth orbit things that we care about, like the Hubble Space Telescope and the ISS and anything between 1 and 300 miles up, if we care about it and need to use it for a long time, we actually have to have small rockets to boost its orbit, which is to say give it a little extra energy since it's lost some orbital speed due to the drag of the Earth's atmosphere.
Okay, the next question is from Victor via email, and I'm not entirely sure the premise of the question is correct, so the premise may need to be corrected as well, or need to be answered. But the question is, I would like to ask, we know that space is expanding and dark energy is increasing. Are these two related? Is the increase of dark energy causing space to expand, or vice versa? So
yes, part of the premise is not how cosmologists describe it. Space-time is expanding, and that is, in the theory of general relativity, that is the manifold. That's a geometric term for space-time, just a pure mathematical term, is what's expanding. The nature of dark energy is interesting because the amount of dark energy, its contribution to the cosmic dynamics, if you like, is constant with space and with time, we think. So I guess I understand the sense of the question, because if space is expanding and there's the same amount of dark energy in every unit volume of space, then it sort of feels like dark energy is growing too. But formally, that's not correct. The amount of dark energy in the vacuum, however you choose to define that, is measured to be a constant as well as astronomers can measure it. It's a repulsive force that it's exerting, a negative pressure, if you like, and that's, we think, leading to the accelerating expansion of space-time. But as a component of the universe, as an ingredient that causes space-time to change its dynamics, dark energy appears to be a constant. And that, of course, is as an allusion to Einstein's gravitational constant, where when he solved his equations of relativity, the term that drops out as a constant of integration, essentially, to get to the technical detail, lambda, does not have any other dependence. It doesn't have a dependence with time or dependence on scale factor.
All right, so Val has a follow-up question to something you discussed earlier. As we look out deeper and deeper into space, we see back in time. And we know the early universe was much smaller than it is now, so we are looking in smaller and smaller space. How can space be flat in this case? It's having trouble wrapping.
Yeah, and that's a good question. If you go far enough back, you're exactly right. Space would not be flat. But you have to go very far back for that. Let's just take it. Let's just take it back to the microwave background. So, because that's radiation, we can see from when the universe was 1,000 times smaller than it is today, and had a temperature of 3,000 Kelvin in the radiation instead of 3 Kelvin. It's a simple linear relationship between size and temperature of that radiation. So we have a lot of information about the universe when it was 1,000 times smaller than it is today. And even 1,000 times smaller, space-time on average is flat. I mean, the universe, of course, remember, is in round numbers, is 100 billion light years across. So if it's 1,000 times smaller, that's still 100 million light years across. So even though the density is much higher, That's still an enormous space compared to the size of the Milky Way. And so space-time is still flat, even that far back. But if you continue to project that expanding universe back much closer to the Big Bang, then indeed space curvature would start to be substantial. And of course, logically, in the singularity, the Big Bang itself, space-time is completely curved over on itself. The space curvature is almost complete. But you really have to go quite close to the Big Bang before, if you could do an experiment back then and there, you would detect space curvature.
All right. Another live viewer asked, given the recent determination that the recurring slope lineae on Mars indicates seasonal flow of salty water, do you have a personal opinion on the likelihood of past life forms on the planet?
It's got to be high, because there's still a pretty good argument about the longevity of shallow bodies of water. So we have sort of accumulating evidence now of seasonal flows. We have evidence of episodic eruptions of water from subsurface aquifers bursting through into gullies and ravines and then just evaporating. And then we have slightly more, not controversial, just controversial in terms of how long it persisted, evidence for shallow seas at the mid-latitudes of Mars. And really, that's a lot of argument as to whether those seas persisted for geological timescales, like hundreds of millions of years, or whether they only persisted for a million years or a few 100,000 years. And that makes a difference. It makes a difference for the question, because the question about life can depend on this. And the critical question, of course, is, given the right conditions, how long does it take to form the first cells and to get life going? If that time is hundreds of thousands or a few million years, then the early shallow seas on Mars, when its atmosphere was thicker, might just not have persisted long enough for biology to take hold. And then we'd be unlikely to see any fossil traces of those microbes even if we went to the right place. If those shallow seas persisted for tens or hundreds of millions of years, we think life on Earth started comfortably in that time span. And so really that debate over how long the shallow bodies of water persisted is critical to whether we think that liquid could have hosted life billions of years ago and might have left microbial traces. Now that's the most important argument, because that relates to the surface. What's the current surface, where we could go, where we can send a rover, where we could pick the best. We got to pick places to send the Mars 2020 rover, which will be much more decked out to detect life than the current Curiosity rover. So that's a critical decision where that rover goes. And obviously we want to send it not just to something we thought was a shallow lake bed, but with something we really thought had the best likelihood of finding fossil microbes should they exist. Now, all bets are off when it goes to subterranean life, because we think the liquid water capacity of Mars under the surface has been semi-continuous for billions of years, including up to the present day. And so there's been plenty of longevity of liquid water in different subsurface parts of Mars. Those are just parts that it's going to be very hard for us to access. The other ingredient in this argument or debate is, what is the chemistry of that water? And of course, it was part of the excitement of the Spirit and Opportunity rovers to find moderate pH values. So they were looking at the salinity and the pH of the minerals that were left or deposited in what we think are sedimentary regions. And now we're doing it in Gale Crater, which we also think was a sedimentary region. And those results are very interesting because they do not find extremely acidic or basic conditions. They find intermediate pH chemistry, which would be hospitable to terrestrial type microbes. So the remaining issue is really the longevity of those shallow bodies of water. And it's possible that modeling will not resolve that issue. We simply just don't have enough evidence going back to tether the models.
Okay, the next question is from Jackie, who is on with us live. The movie Interstellar assumed there would be a 5-dimensional creature. Can you explain a little bit about what is the 5th dimension?
Right, and that was a very big liberty that the filmmakers took, but it's fine. I mean, you know, you're allowed to hang it out over the edge occasionally when you make a movie like that. And there was good scientific advice going into that movie. So there's no plausible way to talk about what biology might be like in more than 3 dimensions, just as there's no real clear way to talk about physics in more than 3 dimensions, because we're talking therefore about brain theory, multidimensional, string mathematical constructs and so on. So the physics of that is possible. I mean, there's theoretical physics that suggests multidimensional spaces are possible. To go from there to biology is a really big step, because even though you might have physical structures in multiple dimensions or higher dimensions, biology implies something else. Biology implies information coding and transmittal. It implies persistence. It implies evolution. And so there's some higher attributes that we allude to with life, with biology, however you could choose to define biology, which we have essentially no basis for understanding whether they could propagate or persist or even be encoded, if you like, in a higher dimension. You might imagine that when you've got extra dimensions, you have lots of degrees of freedom and so liberty to encapsulate or encode all sorts of things. But that's just pure speculation. So I think we're just so far from understanding a general theory of biology that we can't project it into higher dimensions.
Okay, the next question is from Jerry Murphy via email. Does astronomy know if the giant spot, the great red spot on Jupiter, is in the upper atmosphere only, or how far down does it extend, like to the, he says surface in the question.
Yeah, so no, it definitely doesn't go to the surface. So we do know by magnetometry from the space probes that Jupiter, as the other giant planets, has a small rocky core, a super Earth, if you like. The mass of that is debated. It's the best guess is 5 Earth masses as Jupiter's core. But if you visualize a 5 Earth mass core inside Jupiter, that's way down there. That's very far down. And no, the giant red spot it's not a total surface laminar feature. It does extend, I think, hundreds of kilometers deep in the atmosphere, but there's a lot of wind gradients in the vertical strata of the Jovian atmosphere, because the wind speeds are changing rapidly as you go down the atmosphere, and that mixing would lead to disruption of the red spot. So the red spot actually can only persist for the at least 4 centuries that we know it has since the invention of the telescope, by being a fairly shallow feature of the upper atmosphere.
Okay, the next question is again from Jackie. As Newtonian law of universal gravitation can only be applied to 2 bodies, why, when it comes to 3 or 4 bodies, can we only have an approximation of the gravity?
The Newtonian theory is essentially based on this very simple linear equation, which relates the force between 2 objects to the masses of each and the distance between them, with the constant of proportionality being the universal gravitational constant. Now, it would seem that that doesn't completely fall apart when you have 3 objects, because if you put 3 objects in a triangular configuration, you can clearly calculate the force from one on each of the other 2, and so on. But remember, gravity is not a static situation. You're dealing with orbits and motions. So when 2 objects are having their force calculated, they're not sitting there at the fixed distance. Their distance is changing because they're in some orbital configuration. And when you do that with 3 objects, you try and because now essentially, think of it, you have other variables. Basically, you have the variable of distance, x, y, and z, and you have the 3 components or components of the vector of velocity, x, y, and z, for 2 different objects. So you've actually got 12 parameters to solve, and the system is underdetermined. So that means if you try and calculate it, you don't get an exact solution. So that's the simple answer. It's because you're dealing with velocities, and with 3 objects, you simply don't have enough nailed down parameters to calculate it exactly. You can do it with successive approximations as accurately as you want with a big enough supercomputer. And of course, Newtonian gravity is applied in the solar system with fairly high precision, thanks to that. And also in Newtonian gravity, you get to ignore things that are very low mass. So when you're calculating orbits and you have them massive things And other massive things you can essentially ignore. For example, you can ignore the moons of a giant planet when you're calculating how the giant planet moves around the sun, because they're just tiny, tiny perturbations in gravity theory. So gravity theory is based entirely on approximations, because almost every system we can imagine has more than two objects involved. So that's essentially how all calculations are made.
Okay, the next question is from email. We've seen the rise of discovery of thousands of exoplanets. Do you believe that we will ever be able to travel to these distant exoplanets and explore them, and with Mars, colonize Mars?
So the exoplanets, probably not, and ever, of course, is a long time, but I mean in the next within a century, probably not. And that's because most of them are found by Kepler, the Earth-like planets, and those planets are hundreds of light years away. I mean, the nearest Earth clones so far are dozens, mostly actually a couple hundred light years away. That's a phenomenal distance. Remember, a light year is, round numbers, 10 trillion kilometers. So you're talking about things that are hundreds or thousands of trillions of kilometers or miles away. That's just so far beyond the capability of spacecraft, even for robotic miniaturized spacecraft, that we're not going to do this until we can generate near light speed travel of a miniaturized robotic spacecraft, which would still take a lot of energy. And that's just to do remote sensing. I think eventually we will do it. I also think eventually with better surveys we'll get lucky and we'll probably find the nearest Earth clone, which could be in the Proxima Centauri system. That would be 4 1/3 light years away. That's interesting, because at a 10th light speed, which is completely doable with current technology and a miniaturized probe, you can get there in 40 or 50 years, 2 generations. And I think if we found such a nearby Earth clone, we'd do it. But again, and that might happen within a few decades, say. Technology would allow that. So that's really a very hard problem because of the distances. Colonizing Mars is a hard problem just because of the distance, also an 8 months minimum travel time, and the need to protect the lives of the astronauts, and then also sustain an infrastructure on a place that's tens of millions of miles from the Earth. And that's definitely going to be doable, and I think it will be done within 30 years. But it'll take a lot of money and a lot of effort, and it's essentially going to require that we not have to send a lot of stuff with the astronauts, because sending that stuff to Mars requires huge rockets, is very expensive and time-consuming. The best thing to be able to do is to have robotic missions going in advance of the astronauts, essentially fabricating the place that they will live and sort of stocking it more or less, and then having the astronauts go into a situation where they can harvest from the soil the water they need to drink, the oxygen they need to breathe. All this is played out very nicely in The Martian, and I do recommend to people to read the book, because the book has a lot of the calculations. The movie sort of glosses over all the details of the technical calculations that made sort of the Watney character interesting, because he had to solve so many problems. In the movie, he only has to solve, a few problems. In the book, he's solving a problem like every page. And it's that kind of problem. It's how do you get enough oxygen from the rocks? How do you store enough water? How do you rip enough oxygen off the water to make rocket fuel, and all those things? And that's what we'll have to do on Mars, but we'll have to do it on Mars, not take all that stuff with us. But it's not actually that difficult technology. So I do think, as I mentioned, that it'll happen within about 30 years.
All right, and it is almost time for us to wrap up.
Okay, so thanks again. Really great questions, some high-level, very interesting questions this week, and we'll be back again in a week or so. Thanks.